Hi everyone and welcome to EE 326 Lecture 11. Today I'm going to continue our discussion of the differential pair, and I'm going to start talking about the small signal model and small signal behavior of the differential pair. And I'm going to introduce a new concept called the common mode rejection ratio. For your book, this is sections 9.1 and 9.3. All right, let's get started. So we introduced this concept last lecture, the differential pair. The differential pair consists of two transistors, transistors M1 and M2. They have a current source at the bottom. Oops. That we often refer to as the tail current source. And that's ultimately going to be created with a transistor. And we have this model here, this important model here, where we model the output resistance of that current source as R out, indicating that it's not actually going to be a perfect current source. We have two sorts of inputs that we defined. We have what we call a common mode input, and we have a differential mode input. And so we can see we have two inputs on our gates here, VG1 and VG2, to this very symmetrical circuit. The differential inputs are equal and opposite inputs. The common mode input is a common voltage that is the same on each side. And so we can write VG1 as a sum of half of the differential on top of the common mode, and then VG2 as the sum of the common mode and the negative half of the differential input. Okay, and as we introduced last time, if we plot the current through the transistors I1 and I2, the differential with differential inputs, we see this interesting behavior where the current switches from one side to the other depending on the polarity of the ID. And so the current is essentially steered between the two transistors. And it's in this region here in the middle that we really like to operate. From an amplifier perspective, it's nice and linear, and we get gain in this region. So that's where we're going to focus on today. We're going to focus on creating a small signal model for this linear region. All right, so to begin, we'd start out with just a differential pair. Let's not include any loads on there, just the transistors M1 and M2 and our tail current source. So what we'd like to do is draw the small signal model for this. So we see two NMOS transistors, so we can immediately draw the small signal model for those transistors, and then include the other effects like R out, for example. So let's do that. We'll start out with our input here. We're going to have a voltage-controlled current source for transistor M1. This will be positive VID over 2 on the gate on the left, and this would be VGS1 plus minus, and so this would be GM VGS1, and this will have some little RO associated with it. And then coming out here, we'd have some current flowing down, which we'd call I1. Now we can do the same thing for the other transistor. Very symmetric. We have RO. We're going to have our voltage-controlled current source, which is going to be, in this case, GM2 VGS2. And then we'll have VGS2 plus minus. And finally, we'll have minus VID over 2. And the current coming down on this side will be I2. These two are connected, right? We can see the two transistors, the sources are connected, so we'll connect those. And now what about the tail current source? Well, from a small signal sense, what we'll see, this is a DC current here, so that looks like an open circuit, the ideal current source. But we will see the output resistance of that, which I'm going to put in now, and that's going to be, we're going to label that as R out, meaning the output resistance. So that's the small signal model for the differential inputs for our differential pair. Notice we haven't put the loads on yet. We'll do that in a second. By loads, I mean any resistor here connected to VDD. All right, let's move on now and see if we can do some analysis here. So first, let's talk about this voltage here called Vs. It's Vs because it's the source of M1 and M2. And why do we have this R out to begin with? Well, the current source is ultimately going to be created, if we were to redraw that, by a transistor and a current mirror. So this transistor is going to create our current source. And what that R out is really modeling is going to be the behavior of a if we plot the ID versus VDS of this transistor, which is going to create the tail current source, we're going to see some behavior that looks like this, right? And so this will have some nominal I value here and some nominal Vs value here. And that's the operating point, right? That's a Vs and I. But what we see here is that this has a finite slope to it. And so if we have any change in the current, like a small signal change in the current, then we're going to get change in the voltage, we're going to get a small signal change in the current. And so when we wiggle Vs, we're going to have some wiggling on Vi, and we model that with our output resistance R out. And this is all from what we call the tail transistor. And it turns out this is really important to the analysis that we're going to do here for both for the differential mode gain and the common mode gain, as we'll see. Okay, so now that we have our small signal model and we understand where R out is coming from, so here's just the same small signal model redrawn. And the only thing that we've really changed here is that I've split the tail output resistance, the output resistance from the tail transistor, into a parallel combination of resistances to R out. If we have two transistors that are double in value and we put them in parallel, the equivalent of that is just R out. And so what we start to see here is there's some symmetry to our circuit. Our circuit now looks very symmetrical. And you can think about what we call half circuit concepts. That is, can we split this two transistor differential pair into a single side here, split this up, and then do the analysis on one side to make things easier. And again, we're going to have a differential input, we're going to have a common mode input, and we can express our total input as a sum of small signal common mode and small signal differential, just like we did earlier. So what we'll notice, now this is where we're going to try to take advantage of some of the symmetry, is imagine we have a purely differential input, okay? So we have positive VID over 2 on the left and negative VI2 on the right. And let's suppose our input on the left goes up a little. We get some delta V that goes up. What's going to happen? Well, we're going to get some little increase in current in our voltage-controlled current source, right? Similarly, on the right side, we'll get a delta V going down, and we're going to get a decrease in current in our tail current source, which I can draw as a delta I going up on the right, and this would be a delta I going down on the left. So on the left, voltage-controlled current source, we get a little increase in current, and on the right voltage-controlled current source, we get a little decrease in current. And so what we see is that this increase in current on the left is exactly mirrored by the decrease in current on the right. And so what will happen is any change in currents will flow this way, right? And as a result, we're going to have no current flowing through these two R outs. There'll be no current if if we have a strictly differential input, right? So one side goes up, one side goes down, we get this change in current that's linear, and so the decrease on one side is compensated by the increase on the other side, and we have no change in current through to our out. If we have no change in current through these transistors on the bottom, guess what? We have no change in voltage either. And as a result, we can think of this middle node here as a ground. So we have no change in current through the two bottom resistors, therefore no change in voltage. Therefore, we can think of this voltage as not changing at the source, or we can think of it as a small signal ground. And now if we think of it as a small signal ground, we can see that these circuits are essentially separate and independent of each other, and we can do what we call half circuit analysis. But let's keep going on this now that we see this small signal ground, and we can split these two sides up. So the left side would be from transistor M1, and the right side would be from transistor M2. And so we have our positive VID on the left and our negative VID on the right, VID over 2. And so the question is, what's the current that we're going to get? Well, that's to the first order. We could say that I1 is approximately equal to GM, right? Just this value here, GM VID over 2. And same thing on the right, we could say I2 is approximately equal to minus GM over 2 times VID. And so now we can add the load here. We could go up and basically add our load resistances and figure out what our voltage gain is. So if we do that, now we've added RD to both sides, and we just figured out what these I1 and I2 values are, right? In the previous slide, what we can write, if we look at Vout1 from the left side and Vout2 from the right side, we can write that Vout1 on the left side is equal to minus VID over 2 times GM1 times RO1 parallel RD. And so you might be thinking, okay, where did that come from? Well, we know that the current, from the previous slide, we know that the current I1 is approximately equal to GM over 2 times VID. And it's going to be this current flowing through the impedance at that node that gives us a voltage. Right? So this is the current right here. This is I1, and then this is the impedance at the node. And the negative sign comes from the fact that we have a voltage drop across RD. So when the current goes up, our output voltage goes down. And so if I rearrange this, I can write that Vout1 over VID is equal to minus GM1 over 2 times RO1 parallel RD. And if I say, well, let's just assume the output resistances of the two transistors are equal, then I'll say this is equal, and the GMs are also equal, then I would say this is minus GM over 2 times RO parallel RD. So that's for the left side, that's to find out what Vout1 is. We can also find out what Vout2 is in a very similar fashion. This would just be, notice that in this case we have a minus VID input, so we're going to get a positive sign. Otherwise, everything else is going to be the same. And so we're going to get VID, I'll just make it really clear, we're going to have minus VID over 2 GM2 times RO2 parallel RD. And so I can write that Vout2 over VID is equal to GM2 over 2 times RO2 parallel RD. Again, assuming that GMs and ROs are equal, this would be equal to GM over 2 times RO parallel RD. D. Now keep in mind, if we're looking for a differential output, what we're interested in is this differential output voltage here, V out, which would be V out 2 minus V out 1. So if we want to figure out what V out 2 minus V out 1 is, we can just say that we can just write this out. V out is equal to V out 2 minus V out 1, and which we can take from the previous slide. We just say V out is equal to VID over 2 GM times RO parallel RD. So that would be basically V out 2, sorry. And now we subtract from that R minus VID over 2 GM RO parallel RD. And this would be V out 1. And so what we get is that V out over VID is equal to GM RO parallel RD. And what we're going to call this is the differential mode gain, A sub D. Okay, so let's just recap here. This is the differential gain. So just to recap here, what we did is we created a small signal model, right? And then what we solved for was V out differential over VID differential, and that gives us our differential gain. And what we see as a result is very similar to a common source amplifier. It's just GM little RO parallel RD. So that's the differential mode gain. What we also need to think about is the common mode gain. In other words, if we put in a common mode signal to the circuit, how does it behave? And this turns out to be an important metric in circuits. So let's also try to create a common mode small signal model. And we can do that. So here's our small signal model. We've separated our resistors into two resistors again, two parallel resistors that are double in value. That's an equivalent circuit. And so let's try to again create a half circuit to make the analysis easier. And so in this case, we're going to have equal inputs, right? We're going to have a common mode input on the left and a common mode input on the right. So if we get a delta V coming in on the left side that goes up, we're going to get a delta V on the right side that also goes up. They're going up and down together. So if we get a delta V, we're going to get a delta I going down and another delta I on the right side going down, right? And so as a result, we're going to get more current, the same delta I flowing through our output resistance, right? And what we see here, based on symmetry, assuming everything is matching, right, that we're going to get no current flowing from left to right, I equals 0, because everything is symmetric. The left and right side go up and down together. There's no differences in the left and right side because it's a common mode input. So as a result, we have no current flowing, so we can actually eliminate this connection with no change in the way the circuit behaves, right? Now, we can't get rid of R out anymore because we do have a change in current flowing through R out, and so we have a change in voltage there. So we have to leave the 2R out there, but we can separate these two halves of the circuit. If we separate the two halves and we do what's called a half circuit analysis on one side, so now we're just taking one side, and again, what we're going to try to do is figure out what the output current is without a load, and then we can apply this to the other side because of symmetry. So For the case of this analysis, let's just ignore our O for the moment and assume it's not there. So all we have is our voltage-controlled current source and our 2R out value. What we can write is that I out, IO, is equal to GM VGS, right, just from here. Makes sense, right? But the question then is, what's VGS? And that's equal to GM times V common mode, which is going to be on the gate, and that's the VG, minus the source voltage, which would be right here. And so that's going to be our current times 2R out. So that's IO times 2R out. All right, so this is VG and this is VS. The difference between them is VGS, right? And so if we do a little manipulation here, we can write that I out plus GM IO R out is equal to GM VC. This should be a 2 here. Let me rewrite this just to make it clearer. GM IO times 2 R out. So then I can write that IO times 1 plus GM 2 R out is equal to GM V common mode. Finally, I can just solve for I out, and I get GM V common mode over 1 plus GM times 2 R out. So that gives us this output current for a common mode input. Again, we're using the half circuit model based on symmetry. So if we have the output current, then we can add RD back in and figure out what the voltage drop across RD is to get the output voltage, right? And if we do that, we can just write that V out is just going to be the current times the current times the resistance. So that would be minus IO times RD to get the voltage drop across RD. And that would be equal to minus GM VC RD over 1 plus GM 2R out. And so let me just be consistent here, and I'll call this V out because that's what I've labeled in this diagram here. So then I can write that V out over VC, or V out over V common mode, which I'm going to call the common mode gain, AC, is equal to minus GM RD over 1 plus GM times 2 R out, which we can see if we assume that GM 2R out is much greater than 1, then AC would be approximately equal to minus RD over 2R out. And again, this is the common mode gain for our differential pair. So now we get to an important metric for differential circuits, and this is called the common mode rejection ratio. And so what that means, what the point of this metric is, we'd like our circuit to amplify differentially, but not amplify the common mode signals. And so what we do is we define the common mode rejection ratio, CMRR, as the differential mode gain over the common mode gain. So what you'd like is a high common mode rejection ratio, so a high AD, and a low common mode gain, so AC should be low. Now keep in mind, as we're going to talk about next time, there are multiple ways to define CMRR, so we'll talk about a different way in the next lecture. But this is one sort of approach to a common mode rejection ratio. So if we apply what we just found for AD, for the common mode gain and the differential mode gain, we could write that CMRR is approximately equal to GMRO parallel RD. Right, that's the differential mode gain divided by GM RD over 1 plus GM 2R out, which if we simplify this would be approximately GM RD, assuming RD is considerably less than little RO, over RD over 2R out, and this will go away, so this is approximately equal to 2 GM R out for the common mode rejection ratio. And so what does that tell us as a designer? We want R out to be as large as possible, right? And so how do we make R out really large? A couple things we can do. We can make the transistor really long. That increases the output resistance. Or we could actually cascade that current source and give it a very high output resistance. In addition, we'd like our input GMs to be large, but we have less control over the GM than we do out of the output resistance. Okay, well that's it for today's lecture. Thank you very much.